Hey everyone. So today we're going to be taking a look at section 3.4, which is about derivatives. And derivatives are kind of one of the heavy hitters of calculus. I usually break down calculus into three parts. We've got the limits, we've got derivatives, and then we've got integrals. So this is really going to be the foundation for probably the next month or so of what we're going to be doing. So our goal is to calculate the slope of tangent lines as well as take derivatives of functions. And if you haven't had a chance to take a look at the limit sections yet, so 3.1 through 3.3, make sure you rewatch those because we're going to be using stuff from all three sections throughout 3.4. Here in example 1, they're asking the revenue in dollars for the sale of X plastic planter boxes is given by the function R of X equals 20X minus 0.02X squared. And they say that X is bound between 0 and 1,000. Mainly, if you were to plug in 0 or 1,000, it would give you a revenue of 0, and no one wants that, so we're working between those two numbers. So for part A, it asks, what is the change in revenue if production is changed from 100 planters to 400 planters? So what we really need is we need R of, we need R of 100 and R of 400. So that's the revenue of 100 planters and the revenue of 400 planters. Luckily, in our image, they tell us what this revenue is. It's right here. When I make 100 planters, my revenue is 1,800. And when I have 400 planters, I have a revenue of 4,800. If you weren't sure where those numbers came from, we could get them from plugging into here, because this is my revenue equation, but they were nice enough to provide that information. So to answer A, what is the change in revenue? So the change in revenue would be the 4,800 minus the 1,800, which gives me $2,000. And then for part B, they ask, what is the average change in revenue for this change in production? Well, the change in revenue was 2,000, and my change in production, I went from 100 to 400. So it's 2,000 over 300, which, let's see, 2,000 divided by 300 is going to give you 6.67. So each additional planter on average is giving me another $1.67. So what we were calculating on the last slide was the average rate of change in revenue. So to give a more general equation, if y is f of x, and we're calculating the average rate of change from x equals a to x equals a plus h, we would take f of a plus h minus f of a divided by a plus h minus a, which reduces down to f of a plus h minus f of a over h. So if you were to think about this as like the 100 and 400, the 100 plus 300 from the last example, you'd really be looking at f of 400 minus f of 100 over the 400 minus 100 from the last example, and that's f of the 400 is f of 100 all over 300. And it's just a example, like to go back to example 1. So this is the more general equation that we could use. Example 2, it says that a small steel ball dropped from a tower will fall a distance y feet in x seconds, as given approximately by this formula here. Y equals f of x, which equals 16x squared. So here in the image, they tell us that position at 0 seconds is right here at the top. After 1 second, we drop down to 16. After 2 seconds, we're at 64. After 3 seconds, we're at 144. And they want to make the note that we're saying that down is the positive y direction in this case. That's always good to know because vectors and what is positive, what is negative is up for debate. So for A, it says find the average velocity from x equals 2 seconds to x equals 3 seconds. It also reminds you that velocity is the change in distance over the change in time. So they're really asking, well, what is your position at 3 seconds? Well, let's call that f of 3, minus the position at 2 seconds, f of 2, over the change in time. Well, we're at the 3-second mark and the 2-second mark. So f of 3 is 144. We can get that from our from right here, 3 seconds, minus 64, that was 2 seconds. And the change in time is 1. So 144 minus 64, I believe that's 80, over 1 is 80. So the average velocity is going to be 80 feet per second. Feet per second. Part B, it says find and simplify the average velocity from x equals 2 seconds to x equals 2 plus h seconds, where h does not equal 0. Okay. So they want us to find f of x plus h minus f of x divided by x plus h minus x. So the x in our case is 2, so it's f of 2 plus h, f of 2. So f of 2 plus h, we're going to have to plug in up here. F of 2 plus h, well, that's going to be 16 times 2 plus h squared. Now, 2 plus h squared, remember, this is going to have to be 2 plus h times 2 plus h. You can't just distribute the square. So this is going to be 4 plus a total of 4h plus h squared. That h does not show up well here, h squared. So 4 plus 4h plus h squared. And then we've got to subtract f of 2. But we know f of 2 is, oh, and then I forgot to multiply by 16. Oh, goodness, let me get that in there. Because we still have this 16 to take care of. So 16 times 4 is 64. 16 times 4h is 64h plus 16h squared. Now we need to subtract f of 2. So f of 2 is 64. And in the denominator, we have 2 plus h minus 2, so we just have an h. In the numerator, 64 minus 64, those should go away. So this is going to clean up to be 64h plus 16h squared, all over h. Now, one of these h's can come out. This is really h times 64 plus h. For h, so our h's cancel. So we're going to get 64 plus h. And then for part C, they're asking us to find the limit of the answer of b as h goes to 0. So the limit as h goes to 0 of 64 plus h, which gives me a final answer of 64. So on this slide, we have the definition for instantaneous rate of change. So earlier in this section, we were talking about the average rate of change. This is the instantaneous rate of change, which you will find is very similar. The only real thing that we're adding is this, this additional limit here. So it's defined as the limit as h approaches 0 of f of a plus h minus f of a all divided by h. And if you'll recall from some of the previous sections, this is our difference quotient, and we're going to see this come up again and again and again. So if you're not very good with working with the difference quotient, make sure you go back and practice some of those problems, because that's going to be very important going forward. On this slide, they've got some kind of just reminders of facts about lines. So if we wanted to take a look at a line and we've got 2 points, x1, y1, x2, y2, where x1 and x2 are not the same, then the slope of the line that would pass through those 2 points is y2 minus y1 divided by x2 minus x1. So that's something that you'll probably remember from algebra or geometry. And a way to find the equation of a line is if we take one of the points and plug into the point slope form here, where we get y minus y1 equals m times x minus x1, where m is our slope. And we're going to be using these a lot too, because it's one of the applications of the derivative is to be able to find equations of lines. Here in example 3, they say given that f of x equals x squared, they ask us to find the slope of the secant line for a equals 1 and h equals 2, and then again for h equals 1. Okay, so that's a two-parter for part A. So the slope of a secant line, we're going to do f of a plus h minus f of a all over a plus h minus a. So for this particular problem, if we're going to use a equals 1 and h equals 2, it's going to be f of 1 plus 2 minus f of 1 over 1 plus 2 minus 1. So it's f of 3 minus f of 1 over 2. So f of 3, remember f of x is just x squared. F of 3 is going to be 9 minus 1 over 2, 8 over 2, which is 4. So what happens if we make h a little bit smaller? Instead of being 2, let's make it 1. Well, in that case, we're going to be looking at f of 1 plus 1 minus f of 1 divided by 1 plus 1 minus 1. So this is f of 2 minus f of 1 all over 1. So f of 2, 2 squared is 4, 1 squared is 1, over 1 we're going to get 3. So by changing h from 2 to 1, we're going from a slope of 4 to a slope of 3. So for B, they ask us to find and simplify the slope of a secant line for a equals 1 and h, where h is not 0. So we're not going to plug in a particular value for h, we're just going to leave it as a variable. So we're looking at f of a plus h, I guess 1 plus h, we already know that a is 1, minus f of a all over 1 plus h minus 1. And let's see. So what is f of 1 plus h? Well, that would be 1 plus h squared, which is 1 plus h times 1 plus h. So we need to FOIL that out. We're going to get 1 squared plus 2h plus h squared. In our numerator, it's 1 plus 2h plus h squared minus f of 1, because a is 1, so subtract 1, divided by 1 plus h minus 1 is just h. So my 1 and negative 1 of the numerators are going to cancel out. I'll get 2h plus h squared over h. I can factor one of these h's out, so I get h times 2 plus h for h. The h's cancel, and I get 2 plus h. And they say, well, find the limit as h approaches 0 of part B. So the limit as h approaches 0 of 2 plus h, well, that's going to be 2. So going back to our first answer, when h was 2, we got a slope of 4, as up here. When h was 1, we got an answer of 3. And as h got closer and closer and closer to 0, we're getting this final answer of 2. So as h gets smaller and smaller, we're getting closer and closer to a tangent line. A secant line, if you don't remember, let's say I have like a circle. A secant line would touch this twice. So something like this. This is a secant line. And we're finding the slope of the secant line. But as the 2 points move closer and closer together, so this is moving closer, the secant line is becoming closer and closer to a tangent line. And that's kind of what we were seeing here. As we move the 2 points to closer and closer together, as h becomes smaller and smaller, we're getting closer to taking the slope of a tangent line more than a secant line. On this slide, they're telling us the slope of a graph. So this is the slope at any given point on a graph. It says, given that y equals f of x, the slope of the graph at the point a, comma, f of a is given by the limit as h approaches 0 of f of a plus h minus f of a all over h. And that's providing that the limit exists. And the slope of the graph is also the slope of the tangent line at point a, comma, f of a. And that's kind of what we were just talking about in the previous slide, where before we were calculating secants, and we're getting closer and closer to tangents. And this is really the slope of the tangent line to any point on a graph, assuming the limit exists. And then last and not least, we've got the derivative, what this section's all about. So we say for y equals f of x, we define the derivative of f at point x is denoted by, kind of gets smudged together. This is an f with an apostrophe, or we read it f prime. So f prime. And it is defined as the limit as h goes to 0 of f of x plus h minus f of x over h if the limit exists. And we say that f prime exists for each x in an open interval a to b, then f is said to be differentiable on the interval a to b. So if we find a stretch of points that we can take the derivative, we say that stretch of points would be differentiable on that interval. So a little more about the derivative. The derivative of function f forms a new function f prime, and the domain of f prime is a subset of the domain of f, meaning the derivative is either as large as f or smaller than f. F prime will never be bigger than the function that it came from. And then the derivative has a couple different applications. So one way we use it is when we're trying to find the slope of a tangent line. We use it to calculate instantaneous change. We can also use it to calculate velocity. So at least in the Western Hemisphere, we usually credit Isaac Newton for the discovery of calculus. And a big reason why he worked with calculus so much was to explain the physics that he was working on. Calculus and physics are very similar. So if you're taking physics right now, a lot of the stuff that we do in here is applicable in there, and a lot of the stuff you're going to do in there comes directly from calculus. They're basically best friends. On this slide, they give us a 4-step process to taking a derivative. I know that when I learned calculus, they never called it the 4-step process. We just called using the definition of a derivative to take a derivative. But this has been helpful to try to break it down into 4 steps rather than trying to do everything at the same time. So if you look at step 4, this is the definition of a derivative. So what they say is, okay, break it down chunk by chunk. So if we solve for f of x plus h, then we can take away f of x. That would be our step 2. And then the next thing we'll do is we'll divide by an h. And then whatever answer we get after that, we will take the limit as h goes to 0. So this effectively takes one challenging task and turn it into much easier steps. So if you hear someone say use the 4-step process, this is what they're talking about. If you hear someone say take a derivative using the definition of a derivative, this is also what they're talking about. I hope that makes some clarification. Depending on which textbook you're looking at or which professor you have, they can be called either or. So example 4 here, they say find f prime, or the derivative of f at x, for f of x equals 4x minus x squared. So remember, the derivative of this is the limit as h approaches 0 of f of x plus h minus f of x all over h. So if we want to use the four-step process, which is what I recommend, the first thing I'm going to do is find out what is f of x plus h. So in my function, wherever I see an x, I'm going to replace it with x plus h. So this is going to be 4 times x plus h minus x plus h squared. Now x plus h squared is really x plus h times x plus h, which comes out to be x squared plus 2xh plus h squared. And then here for the 4, I can just distribute it. So that's going to give me 4x plus 4h minus x squared plus 2xh plus h squared. So step 2, they say take your f of x plus h and subtract f of x. So remember, f of x is right here. They tell us what that is. So we're going to get the 4x plus the 4h minus x squared plus 2xh plus h squared. And we're subtracting 4x minus x squared. So if you take a look, 4x minus 4x, those are going to go away. Negative x squared minus an x squared, those go away. So this will clean up into 4h plus 2xh plus h squared. And for most problems, here's the first time you can kind of do a self-check to see if you're doing this right. At the end of step 2, you want everything to have an h in it. If it's a fraction, you at least want everything in the numerator to have an h in it. So if you take a look, I've got 3 terms, 4h, 2xh, and an h squared, meaning every term does have at least one h here. And the reason we want that is in step 3, we're going to do f of x plus h minus f of x all over h. So this is going to be 4h plus 2xh plus h squared all over h. And I want to be able to take an h out of the numerator. So if I take an h out, I'm going to get 4 plus 2x plus h all over h. These h's will cancel. And then for my last step, I'm going to take the limit as h approaches 0 of f of x plus h minus f of x all over h, which is going to be the limit as h approaches 0 of 4 plus 2x plus h. And now if I plug in 0 for h, the only thing I have is I'm going to get 4 plus 2x. And that is my final answer. So it looks like a lot of work. If you step back and you take a look at the work, it's like, wow, I had to do a lot there. But if you really break it down, step 1, step 2, step 3, and step 4, hopefully these bite-sized chunks will make this feel a lot easier. The other thing I'd like to remind you is really at step 2, at the end of step 2, make sure that all of your terms have an h left. That is going to be a good sign that you're doing things correctly. And these things just take practice, practice, practice. The number one mistake that I'm going to see people make are with arithmetic errors and algebra errors. For example, here, I don't know how many times I've seen someone just write that as x squared plus h squared rather than what it actually is equal to, x squared plus 2xh plus h squared. So if you're making some mistakes, you might need to review algebra a little bit, but this is the process. There are some problems that are easier than this, there are some problems that are harder than this, but this is a good baseline problem to get used to derivatives. Example 5 here is actually going to build off a result from example 4. So it says in the last example, we started with the function f of x equals 4x minus x squared. And we found the derivative of f at x to be f prime of x equals 4 minus 2x. So the slope of the line tangent to the graph at any point x comma f of x on the graph is that slope m equals f prime of x which equals 4 minus 2x. This is our big takeaway. Our slope at any point on the graph is this. So for A, it says find the slope of the graph at x equals 0, x equals 2, and x equals 3. So that's pretty easy. It's actually going to just be f prime of 0, f prime of 2, and f prime of 3. So if you plug in 0 for f prime, you're going to get 4 minus 2 times 0, which is 4. If you plug in 2, you're going to get 4 minus 2 times 2, which is 4 minus 4, or 0. And if you plug in 3, you're going to get 4 minus 2 times 3. So 4 minus 6 is negative 2. So then for part B, they ask find the equations of the line tangent to f at all indicated points. Now that might be hard to do on this limited amount of space, but let's check. So we know that this is the first slope, the second slope, and the third slope. And one way to find the equation of a line, it's y minus y1 equals m times x minus x1. So I know the slopes, because I'm going to get 3 different answers. So I've got 3 different slopes. But I don't have a point, but I do have the x value. This is x. So I could call these like x1, 2, and 3. But now I need to find their corresponding y's. So to find y, just remember that f of x equals y. So if I did f of 0, that would give me the first y value. So here's my f of x. If I were to plug in 0, I would get 0. So the first point I'm going to look at is 0, 0, with a slope of 4. For the second point, I'm using x equals 2, so f of 2, plugging in up here again. I'm going to get 4 times 2 is 8, minus 2 squared is 4, so 8 minus 4 is 4. So that gives me the point 2, 4. And this slope is going to be 0. And then if I were to plug in 3, f of 3, 4 times 3 is 12, minus 9 is 3. So it's going to be the point 3, 3, and I have a slope of negative 2. So for the first one, it's y minus y1, so minus 0, equals m, 4 times x minus x1, which is 0. So this is going to be y equals 4x. So that's my first tangent line. For my second one, again, it's going to be y minus y1, so y minus 4, equals m, which is 0, times x minus x1, which is 2. Now, y minus 4, anything times 0 is 0, so y equals 4. And for the last one, the point is 3, 3, with a slope of negative 2. So I'm going to get y minus 3 equals negative 2 times x minus 3. And we can leave the answer like that. We don't have to do anything else. So these would be our 3 answers. And we're going to see a couple more problems like that on the homework. So make sure you know where this slide is if you have to go back to it. All right, example 6. Now this one is a bit of a tricky one. We have seen a problem like it before using limits, but it's been a while, maybe a few videos. So we're trying to find the derivative of f of x equals the square root of x plus 2. So remember, a limit is, or not a limit, a derivative is the limit as h approaches 0 of f of x plus h minus f of x all over h. So the first step is find f of x plus h. And that would be the square root of x plus h plus 2. Our second step is find f of x plus h minus f of x. That's the square root of x plus h plus 2 minus the square root of x plus 2. And the problem that we run into here is we don't have a lot that cancels. The plus 2 and the plus 2 are going to cancel because it was a minus. But now we have the square root of x plus h minus the square root of x. And that square root's preventing us from canceling out. So we're actually going to have to do a trick which boils down to the difference of squares. And that is something that's usually covered in Algebra 1 and Algebra 2. So what I'm going to do is I'm going to take my square root of x plus h minus my square root of x and multiply. I'll multiply by the exact same thing, square root of x plus h plus the square root of x, or the square root of x plus h plus the square root of x. So something to note here is because this is a minus, I'm putting a plus here. If it had originally been a plus, my second time would be a minus. And then the reason I'm dividing by the square root of x plus h plus the square root of x is, if you think about it, this whole thing here, this whole thing boils down to 1, and you can always multiply by 1 and not change anything. So if you want to, you can add a denominator here of 1 just to help with the multiplication. But when we do this, we're going to get the square root of x plus h minus the square root of x times the square root of x plus h plus the square root of x all over the square root of x plus h plus the square root of x. And if you go ahead and FOIL this out, you're going to end up with x plus h minus x, so no more square roots in the numerator, all over the square root of x plus h plus the square root of x. And now in the numerator, we can actually cancel out the two x's. We've got x plus h minus x, which is going to give us just h. And in the denominator, we're going to get the square root of x plus h plus the square root of x. So that takes us to step 3, and we're running low on room. But step 3 says take the answer from step 2, f of x plus h minus f of x, and divide it by h. So I'm taking this answer here, and I'm going to divide everything by h. If you want to think of it, this is really h over 1. How do you divide two fractions? You flip and multiply. So to flip and multiply, this would be 1 over h, and my h's will cancel, giving me a final answer of 1 over the square root of x plus h plus the square root of x. And then for step 4, which really finding a place where this is difficult, 4, we're going to take the limit as h goes to 0 of f of x plus h minus f of x all over h. So over here, wherever I have an h, this is going to become 0. So I get 1 over the square root of x plus the square root of x, which gives me the final answer of 1 over 2 square root of x. I know that's kind of hard to follow because we had to use the difference of squares, but that's usually about as challenging as these things get. In theory, there are like difference of cube problems and things like that that they can throw at. I mean, anything that you covered in algebra is technically fair game here. But in my experience, this is usually the most challenging type of problem that they would throw at you. So if you can master that step 2, you should be golden here. But again, the name of the game here is really just practice, practice, practice. That will make your life so much easier. All right, example 7. Now this will look just like our previous example where we got a square root. Before we had another number outside of the square root. This one's in the square root, but it's all the same in the end. So we're taking a derivative. So remember, this is going to be the limit as h approaches 0 of f of x plus h minus f of x all over h. So step 1, what is f of x plus h? Well, that's going to be the square root of x plus h plus 4. Step 2, f of x plus h minus f of x. That's the square root of x plus h plus 4 minus the square root of x plus 4. So same issue that we had in step 2 last time. We have square roots, so we can't really cancel anything out. So we'll go ahead and put this guy over 1, and we're going to multiply by the square root of x plus h plus 4 plus the square root of x plus 4. Divide by the square root of x plus h plus 4 plus the square root of x plus 4. And we're going to multiply these guys together. So just extend this fraction bar, add some parentheses. This is my answer. X plus h plus 4 minus the square root of x plus 4 times the square root of x plus h plus 4 plus the square root of x plus 4. We got to do FOIL. So if you think about the first multiplication, the square root of x plus h plus 4 times the square root of x plus h plus 4, the square roots are going to go away. The second multiplication and the third multiplication, because of the opposite signs here, they cancel each other out. So even though they still have square roots, they're going to cancel each other out. And the last multiplication, square root of x plus 4 times square root of x plus 4, that should just end up being x plus 4, but with a minus sign in front because minus times a positive is a minus. So how will this all reduce? We're still in step 2 here. We're going to get x plus h plus 4 minus x plus 4. And then the denominator is still the square root of x plus h plus 4 plus the square root of x plus 4. So in the numerator, my x's go away and my 4's go away, leaving me with just h over the square root of x plus h plus 4 plus square root of x plus 4. And that takes us to step 3. And everything starting at step 3 should be a little bit easier. Step 2 is really the doozy. So this is where we divide everything by h. So h over square root of x plus h plus 4 plus the square root of x plus 4. Well, we've got to divide by h. And we can say that's h over 1. We can move this and flip and multiply, so this is 1 over h. H's will cancel, and I get 1 over square root of x plus h plus 4 plus the square root of x plus 4. And then my final step is to take the limit as h goes to 0. So step 4, the limit as h goes to 0. So I get 1 over x plus, well, h is 0, so I'm going to get 4 plus the square root of x plus 4. So this is 1 over 2 square root of x plus 4. That is my final answer. So these square root ones are definitely a doozy. So practice, practice, practice. They get better with practice. This slide talks about the non-existence of a derivative. Now, the derivative does not exist everywhere. One way to think of a derivative is it's the slope of a function. So what if you get a function where you can't take the slope? Like, for example, a peak like this. What would be the slope at the top of the peak? Well, it looks like it's positive if you come from the left. It looks like negative if you come from the right. So we would say that it's not differentiable. So essentially, you will run into instances of things that you can't take the derivative of. And if you do that, you just say the derivative does not exist. It's impossible to describe all the ways that this could happen. But one way to know is if the limit doesn't exist or if the function isn't continuous. We're going to take a look at a couple different examples on the next slide. But just keep in mind that even though we're learning about derivatives, the derivative cannot be used everywhere. We will run into issues. So continuing to talk about derivatives that don't exist, here are 4 different examples where we're going to run into derivatives that don't exist. If it's not continuous at a point, so like we have a discontinuity here, then we can't take the derivative at A. If you get something really weird, like the graph has a sharp corner, like here, well, we definitely can't take the derivative because if you try to look at the tangent line, one tangent line here looks like it's a positive slope, or the other tangent line looks like it's a negative slope. So taking the derivative here, it wouldn't yield any results. If we, for some reason, had a vertical tangent line, like just straight up and down here, I mean, that's an undefined slope, meaning that the derivative would have to be undefined. And then in the fourth example, or example D, we also run into another example of a vertical tangent line where we just wouldn't be able to take our derivative. So in the next section, I believe we're going to learn about where we know there will be a derivative, and that way we kind of can stay in the realm of things that have derivatives. So some closing thoughts. Well, congratulations to making it this far. The derivative is probably the most different than anything you've done so far. It is a large part of what we are going to be doing for like all year. Even when we talk about integration, the derivative will come up as a regular concept. And what I can say is it does get easier. Doing limits by hand with the four-step process is honestly not how we're going to be doing derivatives even in just a few weeks. We're going to take a look at certain examples where we could have shortcuts, and it'll probably get to the point where a lot of the problems that you did today, you'll actually be able to do in your head using some of the stuff that we're going to learn. So if you're thinking this is difficult and you're not sure if calculus is right for you, don't fret. Keep practicing these problems because you're kind of at a difficulty peak. It gets easier going forward. So keep that in mind as you're doing your homework, that at least for like the next few weeks, this is probably the hardest that it'll be. So if you can get through this, you can definitely get through the rest of the semester, no problem. But again, if there are issues on the homework, feel free to ask. Send me an email, message in Google Classroom, or just ask in class. Other than that, good luck. The homework should be up shortly. And yeah, derivatives, it is a big part of what we're going to be doing. So make sure that you really understand.